Welcome to the Iowa caucuses. No, just kidding. This will be better. Today, before I introduce the speaker and before I say a little more about the lecture series, I want to introduce you to Bruce Bailey, and I'm going to actually have you all do a little bit of science. So Bruce Bailey is a professor of mathematics, and he's also the driver of a thing called the physics bus. And the physics bus drives around the world, actually around Tucson, teaching our students science, K through 12. So Bruce, what do you have for us tonight?
Well, thank you, Joaquin. I was about to ask if I'm microphoned, but yes, I am. And I'm a mathematician. That means I have serious science teacher envy. And this is my opportunity to do a little science. In fact, I'm going to show you how we do science here in the College of Science. And this is some of our most important technical equipment, right? Out of every 10 good ideas we have one really good idea, the rest go in here. And also, we sometimes find that one of our sources of good ideas is our colleagues' trash cans. So, we're going to do a little experiment here, see if the smoke detectors in the auditorium are turned on. Really, this is a little aerodynamics experiment or demonstration, and it also illustrates the fact that if you really want to do science, you have to be able to see what's going on. That's why we make the most powerful telescopes right here in Tucson, and everything else that makes the invisible visible. But now we're going to do an experiment, a math experiment, an experiment involving shapes. Could we influence the shape of a smoke ring by changing the shape of the hole it comes out of? Anybody that has made holiday cookies using a cookie cutter knows that if you use a Christmas tree-shaped cookie cutter, you end up with Christmas tree-shaped cookies. Apparently, the cookie cutter principle does not apply to toroidal vortexes. But then, why should we be surprised? Nature has a tendency to make things round. It makes cells round, it makes planets round, it makes soap bubbles round, even if you blow them out of a square-shaped soap bubble blower. And how many of you ever ordered a pizza? What shape is the box? What shape is the pizza? So, you might think, like soap bubbles or pizzas, that it's always round, whatever the shape of the orifice. And when you think you know the answer, that's the time to do another experiment. That's when you have to wait for your smoke machine to warm up again. If it doesn't warm up soon, you'll have to join me at the second location at 8 o'clock. There we go. That's really the way we do science. Things never work out quite the way you expect, even when they worked twice before. And now we're going to see what happens when you, instead of having a square, you just make a slight change into a rectangle. not only do we not have circles anymore, but they're not even the same shape all the time. They have not only gone into the third dimension, they've gone into the fourth dimension. They are changing with time. And now I would like to say thank you very much. Please give your attention to our speaker.
If any of you want to sit in the Galileo circle seats in the front and you know the answer for that, what happened there, write it in a piece of paper in the back with a $1,000 check, and you can sit in the front seat. I want to thank let's see, where is he? I want to thank our underwriters. Again, I must thank them because they've been with us since day one, just like you have been. The Agnes Nels Henry program, the Arizona Star, Blue Cross Blue Shield, Galileo Circle, these are the members of our community that so handsomely support the college so that we can give scholarships and fellowships to our students and create programs like this. Godat Design, who makes all these beautiful diagrams, the Halualoa Companies, Marshall Foundation, where all these restaurants that you eat around here that are so wonderful, Nguyen Tarbit Patent Law, and Raytheon, that's been a great supporter as well, Research Corporations, and Vantage West. And please thank all of these underwriters. Last week we heard about the oceans. Today we're going to hear about the atmosphere. And in a pivot a bit, after we hear how the atmosphere is reacting to the warming of the planet, we're also going to hear about the consequences of that on our food supply. And it's my great pleasure, in fact, to introduce today's speaker, David Battisti. He's the Tamaki Endowed Chair of Atmospheric Science at the University of Washington. His research is focused on understanding the natural variability of the climate system, with a particular interest in understanding how the interactions between the ocean, atmosphere, land, and sea ice lead to variability in climate on timescales from seasonal to decades. David's presently working to improve the El Niño models. We are now understanding El Niño, and their forecast skill to understand the mechanisms responsible for the drought cycles in the Sahel and to better understand the monsoons. He's also working on the impacts of climate variability and climate change on the food production in Mexico, Indonesia, and China. His research interests are in paleoclimate, in particular the mechanisms responsible for the remarkable abrupt global climate changes evident throughout the last glacial period. Dave has served in numerous international science panels and committees. He is well recognized in the community as one of the leaders in atmospheric sciences. Please help me welcome Dave Battisti.
Thank you. Thank you, Dean Rees. Thank you, everyone, for coming tonight. In my wildest dreams, I never thought I'd be talking to 2,000 people about science. It's phenomenal. I can't believe this community. It's just amazing. Tonight I'm going to talk about global warming and global food production, climate warming, global food production. The projections for the next 35 years that we're going to have to double the world's food supply, mostly grains, to meet the demands of a growing population, and populations that are developing are going to eat higher in the food chain. To do that, we have to increase yields at a rate that was only achieved once in human history for a 20-year period at the end of the Green Revolution. Only we have to do it over a span that's twice as long. We also have to do it in the face of stresses that were not existing during the Green Revolution, okay? Land. Pretty much up through 1960, most of the increase in food production was you just clear more land. You have great land out there, good soils, you clear more land, you can grow more food. Since about 1960, we pretty much used all the land that's good agricultural land. And in fact, we're losing that land at about a rate of 1% per year due to soil erosion, wind erosion, and salinization associated with irrigation. So increasing the land that you're producing food on is not really an option. Water, already limiting in a lot of areas. including here, I suspect. And I should say in the Green Revolution, there was 3 ingredients: better genetic materials, new genetic materials, increased irrigation, and the other one was energy and nutrients. In particular, nitrogen that came online pretty inexpensively. Well, nitrogen is more expensive. The other limiting nutrient is phosphorus, which people estimate has a world supply left of about 50 to 300 years, depending on how you count. So we have 2 stresses there under nutrients. Energy, during the Green Revolution, was incredibly cheap. It's relatively cheap right now, but not compared to the Green Revolution. And of course, it's going to get more dear as the economies pick up again and people use more energy. Energy is important because, in part, you create nitrogen from a process which is more complicated than I understand. And it's also cheap to pump water out of the ground, which is a very expensive thing to do. So it was important for the irrigation. The other part, which is new, is the climate is changing. And as I'll talk to you today, the climate change is an additional stress in this problem. Before we start, let's just reflect on who are the people today that are food insecure. There's about 1 billion people in the world right now that are food insecure, meaning they don't have enough calories on a day-to-day basis to live healthy lifestyles. They live in these countries that are colored here, mostly in the tropics and the subtropics. Now, I'll just define this now. In my field, climate science, we define subtropics as basically between 30 degrees, 35 degrees south and 35 degrees north. And then the tropics, the deep tropics, is right around the equator. That's where these people live. The other important point is, what do they eat? They eat lots of different things, but 50% of their calories is just 3 grains: rice, wheat, and maize. They're food insecure. They're also the poor. So most people in these countries that are malnourished, most people in these developing countries don't own the land they're working, right? They work for someone else to create income, and then they buy the food. So they depend on agriculture for both income and food. Okay, so that sets the stage. And what I'm going to show you here at the beginning is just a brief history of climate change science. What happened in the 20th century, and how do we know why it happened? And what's going to happen over the next 100 years. And then we'll talk about what those climate changes are, what they mean for food production. I'm just going to focus on the things that in the climate science community we're quite confident of. The results are insensitive to uncertainties in the models, for example. And I'm only going to focus on things where we really understand those results. We understand why the changes are going to happen the way they happen. And these are all summarized in these so-called IPCC reports, the Intergovernmental Panel for Climate Change, which basically every 6 or 7 years or so summarizes the state of climate science. Okay. So greenhouse effects, it's really not a new problem. Joseph Fourier, a mathematician, to Bruce, wherever he went to, in 1827 recognized that there was gases in the atmosphere that trapped heat, and that if you took those gases out, that the planet would be much colder. So that was almost 200 years ago. And then this guy Tyndall in 1960 recognized what the gases were. They're water vapor and carbon dioxide. There's a lot of nitrogen in the atmosphere. 80% of the atmosphere is nitrogen. About 19% or 18% is oxygen. But those are not the greenhouse gases. So even though there's a lot of stuff in the atmosphere, it's just these things that are around in small quantities that actually keep us warm. Okay. Then this guy Högboom, Swedish guy, calculated that the amount of carbon dioxide added to the atmosphere due to the burning of coal, right? This was like the Industrial Revolution. His colleague, just right next door, Svante Arrhenius, was a chemist. He estimated, well, at that rate of burning coal, carbon dioxide would double in the atmosphere in about 3,000 years. And then he went and he calculated, well, if we did that, if we doubled carbon dioxide in the atmosphere, what would happen to the global average temperature? And he calculated that it would increase by 5 degrees Celsius, or about, someone do the math for me, 9 degrees Fahrenheit. Global average, year in, year out. Well, it turns out he was pretty much right, okay, where that's in the ballpark, 5 degrees of what we think today. Okay, it's a little bit on the high end, but it's in the ballpark. And he did this with a quill. in a paper. It's not complicated, right? It's not complicated. But he was really off on how long it would take to increase to double CO2. Okay. This is a measure of carbon dioxide measured in the atmosphere from 1958, when I was 2 years old, to last month. And it's just up, right? With little oscillations, which is basically the planet breathing. It's the plants growing in the spring, taking carbon dioxide out of the atmosphere and giving it back in the fall as the leaves and stuff rot. And then there's this trend, okay? We measure carbon dioxide in terms of parts per million. If I grab 1 million molecules of air here, and I count up the number of carbon dioxide molecules, when I was 2, it would have been 316, and today it's 400. Remember that number, 400. It's increasing today because of burning of fossil fuels. There's lots of ways you can prove this is true. No one contests this number. About 90% due to the burning of fossil fuels, coal and oil, and about 10% due to the land use change, clearing forests, right, where you lose the organic material and the carbon locked up in trees and replacing them with fields. It's increased 25% since 1965, 10% since 1995. And you can see there's a little bit of an upward trend here. It's not linear. It's increasing. The rate of increase is increasing. Here's a measure of the global average temperature. Each dot is for 1 year, average over the whole globe. And if you go back here in 1880, here's the temperature, and it's bopping up and down, right? And it's bopping up and down, and it's bopping up and down, and as carbon dioxide has gone up, the temperature has gone up, until here we are last year. It's gone up 1 degree Celsius over this record, right? 0.85 degrees Celsius over the 20th century, and another 0.15 degrees in the last 15 years. This is the uncertainty in the measurement. So this difference here is not the fact that we don't measure temperature well. We measure it quite well. The up and down, so the up and down is due to year changes, like El Nino makes the world about 1/10 of a degree warmer for a year, and then it gets colder again. And then there's volcanoes that go off that put aerosols in the atmosphere that scatter sun that make it a little bit cooler for a year or two. But overall, this trend here is only explainable due to the increase in carbon dioxide, and it's exactly consistent with what we expect when you increase carbon dioxide the way we've increased it. Now, not all places have warmed equally. So the world average increase is about 1 degree Celsius. But if you look at this plot here, you see that the continents in general, there's a little bit of purple up here, right, which is almost 2 degrees. And there's a lot of reds, and the oceans are kind of more oranges. So the land warms more than the ocean. The Arctic is warming faster than, say, the tropics. All these things are exactly what you expect when you increase carbon dioxide in the atmosphere. So not just the global average temperatures increase, but the pattern of change, the spatial pattern of the trends is exactly what you expect when you increase carbon dioxide. The other thing is, you don't have to believe the climate models if you don't want to. The glaciers worldwide are retreating. There's only one way to explain that. The planet's got to be warmer. Right, you could say, well, maybe the wind's blowing from a different direction, bringing warm air in here, and some of the glaciers, like in the Cascades where I live, are retreating. But if I'm bringing warm air into the Cascades, I've got to be bringing cold air somewhere else. You have to conserve mass. So when the glaciers decrease everywhere, the only explanation is it's warming. The whole planet's warming. Snow cover in the Arctic sea ice has decreased. And if you measure the amount of energy in the climate system stored in the ocean, I think Joellen might have mentioned this last week, it's increasing. Now, you have to conserve energy, right? So the only way to increase it is more energy has to be trapped in the system. The only way we know how to do that is to increase greenhouse gases. So all evidence points to it's warming due to increase. It warmed over the 20th century due to increased greenhouse gases. Now here's an experiment. The black line here is the observed temperature trend over this period, here starting in 1860. It goes up about 1 degree. The blue line, the blue solid line, is if I take all the climate models that were used, say, 7 years ago, and I integrate them forward, and I give those climate models only information about how the solar insolation has changed due to sunspots, And when volcanoes go off, they put a little aerosols in, cool the planet a little bit. I find out that the models actually give me this blue line, which goes along here. It just goes along here, and just keeps going along here, and yet the observations are going up, up, and up, and up. If I do the same thing with the models that were used 2 years ago, just go back and they're new models, they've been improved. You go back and you do the same calculation, you get the same answer, right? It just kind of goes along here. That's the response to a volcano, right? It just stays flat. Each one of these other lines is just an individual model. So temperature is going up, but if we only include volcanoes, sunspots, you can't explain that. But if you include the human and natural forcing together, the volcanoes, the sunspots, and carbon dioxide increase, you get exactly what you saw. Right? Now, what we know from this, if you go through all the science, and the science really hasn't changed very much in the last 15 years. And it shouldn't. It hasn't. I mean, Arrhenius did the calculation 120 years ago this year and got pretty much the same answer. The trend in global average temperature is consistent with what is expected due to human forcing, mainly the increase in carbon dioxide. It is much too large to be explained by natural variability or natural forcing like volcanoes or sunspots. All of the observed 20th century temperature trends are consistent with the model's response to the observed increase in greenhouse gases and aerosols. So we've not only increased greenhouse gases, which warm the planet, through industry, burning of coal, we put aerosols in the atmosphere like volcanoes do, which tend to cut down some of that warming. So the estimates are that basically the warming would have been another 1/3 beyond what we saw if we had not let the aerosols, go into the atmosphere at the same time. So the 20th century warming due to increased greenhouse gases has been partially offset by this aerosol loading, we call aerosols. Okay. Historical view. So these international assessments that summarize the state of science, the first one was done in 1990, and they concluded at that time, little observed observational evidence for a detectable human influence on climate. That's simply because the warming really hadn't started to take off yet. The data sets weren't great. People hadn't been looking at them really carefully to make sure that the bad data were kind of found in the data sets. Like if you have a ship recording the temperature and the ship turns out to be in the middle of Moscow, it's like someone reported something wrong, right? And this happens all the time. So you have to go in and kind of clean up the data sets, and climate scientists have done that. Skeptics have done that. You still come up with the same trend there, so nothing changes, right? In 1995, 5 years later, the conclusion was the balance of evidence suggests a discernible human influence on global climate. This is a time when the United States, where I think most people got involved in this problem, and I got involved because I didn't believe the statement. I thought the models were too primitive at the time, the data sets hadn't been cleaned up yet, and the trends just were still relatively small, and a lot of scientists got involved in the US because scientists love to prove things are wrong. Right? And 5 years later, most of the observed warming over the last 50 years is likely greater than 66, 2/3 chance to have been due to increase in greenhouse gas concentrations. 2007, the fourth assessment, most of the observed increase in global average temperature since the mid-20th century is very likely, greater than 90% chance, due to the observed increase in anthropogenic greenhouse gas concentrations. And then, here we are, the most recent report comes out with a human influence has been detected in warming of the atmosphere and the ocean, in changes in the global water cycle, in reduction in snow and ice, in the global mean sea level rise, and in changes in some extreme climate extremes. This evidence for human influence has grown since the last IPCC report. It is extremely likely, that is greater than 95% chance, those are good betting odds, right? That human influence has been the dominant cause of the observed warming since the mid-20th century. Shouldn't be a surprise. Arrhenius got the answer 120 years ago. How much carbon dioxide will be, so if we want to know where we're going, we need to know two things. How much warming will we get for a given amount of carbon dioxide in the atmosphere? And how much carbon dioxide are we going to put in the atmosphere? That question is not a science question. It's a society question. It's something that's decided by people who run energy policies, people run government policies, regulations. It depends on how many more people we add to the planet. It depends on whether governance on these issues is going to be regional, national, global, right? And people get together every, say, 15 years and come up with these projections, and they're all over the place. But we can actually make a pretty good estimate here. I'm going to ask you guys to do this. How many molecules of CO2 in the atmosphere today? 400. Let's say the global population increases by 30% from 7.3 billion to 9.5, which is the current estimates, and they've been pretty stable for a little while now. Let's say all those people develop, including the new people we added to the planet, which are almost all going to be added in developing countries, and they develop and they use more energy, so they have better lifestyles. And let's assume that they do that, and the total emissions per year of amount of carbon dioxide in the atmosphere does not change. What do you think the odds are? 0, right? That's a pretty conservative estimate of how much CO2 in the atmosphere. So we can actually do this calculation. 400 today, two are going in every year. And it's 85 years between now at the end of the year. 2 times 85 is 170, right? So 170 more. We're at 400, we end up at 570. Okay, so there we go. There's the math. It's the only equation I'm going to show you today. Sorry, Bruce. Okay, so here are the three different projections. They're kind of like the extreme projections of these families that wanted to get demographers and policy, energy people together, and they come up with the possibilities. Here we are today at 400 in 2015, 2016. Here's 2100, and we just did the calculation that with that scenario, where we add 30% of the population, they all develop and use more energy, and we don't increase CO2 emissions, we end up with 570. So here's one of their scenarios that ends up at 550. I call that utopia, right? Or dreaming, or whatever you want to call it, okay? But then there's another one, which is this red one, which is business as usual. It's assuming that we keep on developing, we add these people, certain countries move, to renewables faster than other countries, and you end up with more like 900. And then you can do split the difference, which is the green line. And I'm going to show you just results for split the difference, okay? So, and we'll talk about this in a second. Just for reference, if you wanted to, say, only have enough emissions per year so that carbon dioxide didn't change, so nature could actually pull the molecules out the same rate we were putting them in, every one of us would be allowed 300 kilograms of emissions per year, right? Right now, every one of us on average emits 20 tons, right? That's why this is a problem. It's the fundamental energy source that runs the world's economy. And really, if you want to stabilize carbon dioxide, you have to reduce emissions by about a factor of 50. It's not a science problem. It's an issue of what do we do, right? Which is a value statement. Okay, for reference, I just showed you that we've gone from 320 to 400. I'm spending too much time on the climate science, but it's my specialty. Okay. 800,000 years ago, we know this not because there was a guy, a caveman or something like that. Actually, there's no people here, right? Measuring carbon dioxide, but you can go down to the ice and pull out air bubbles and just measure how much carbon dioxide was in the air 800,000 years ago. And you find out that it's been going up and down, up and down, up and down. Each one of these downs is an ice age, where you have 3 kilometers of ice sitting over northern North America. And each one of these ups here puts us at about 260 or 280. And here's all of human history, basically, of agricultural history, from the beginning of agriculture to present, where carbon dioxide basically was around 280 per mil. 80 parts per thousand. Okay, that's where we are today. Okay? So, atmospheric carbon dioxide, if you look at it, we only have ice cores that go back so far, but there's a lot of strong evidence that carbon dioxide hasn't been this high in at least 3 million years. The other thing that we don't know is that it's mainly this high. It's gone up over the 20th century because of burning of fossil fuels, mainly, and some descent land use, clear land. The rate of change is 100 times faster than nature. We know what nature can do. The rate of change in this last 150 years is 100 times or more faster than nature can do it. And the time it takes to restore, if we just stop emitting everything today, CO2 to pre-industrial levels back here, is on the order of thousands of years, okay? So once you put it in, basically it stays. I mean, it's there. You're stuck with it. So then the question is, where are we going? Well, we did this calculation. Utopia is there, right? Split the difference is there, which, by the way, if you project the Paris Protocol out, you get roughly about there. And that's business as usual. Okay, so we're really kind of in uncharted territory as far as humans experiencing climate is concerned. So now, in 2007, IPCC had these scenarios. The business as usual was called A2. Now it's called RCP 8.5. Don't worry about it. It gets you to the equivalent, if you include all the increase in greenhouse gases, methane, everything else, about 930 equivalent carbon dioxide molecules. The global average temperature goes up by 3.4 degrees Celsius. If you do utopia, it's now called RCP 4.5, it goes to 530, and the global average temperature increases by 2.2, and if you do split the difference, it goes up to 2.8 global average. We'll skip this for a second. Okay, so if you swap the vocabulary for what the emission scenario is called, and you find that the results and conclusions from 2007 are no different than they were from 2013. The 2013 report adds one more scenario that says, that just to show you how difficult it is to keep the global average temperature increase less than 2 degrees. Otherwise, there's really nothing new of policy consequence. Okay, the other point I want to make here, and I'm not going to go through the slide, is even if we know exactly how much CO2 is going to the atmosphere, if you give it to all the climate models, they all do the same pattern of warming. Land warms more than ocean, high latitudes warm more than tropics, but the total average warming will be different from one model to the next, okay? And that's simply because we don't fully model clouds from F equals ma, which is Newton's law, right? You just don't have the computer power to do that. So we have to have some rules, it turns out, of like how cloud would change, and every climate model has a different rule for that. And so the total temperature change on average is different, but the pattern is the same, and it's been the same for the last 30 years, since we've been doing this calculation. Okay, with a climate model. So here's the picture of the global average temperature increase for this split the difference emission scenario, not utopia, not business as usual. The global average is 2.8. The point here again is, as I said before, it's not everywhere the same. Land warms more than ocean. The Arctic warms the most. And the other thing I want you to take away is that the numbers here over land are more like 3 or 4. So if the global average is 3, basically multiply by 30% more to get the land average temperature change. Okay. Now, if you're an optimist and you think you can hit utopia, it's the same map. Just multiply everything by 0.8. And if you're a business as usual kind of person, just multiply everything in this map by 1.2. The pattern is the same across every climate model. Okay. Now, when it comes to precipitation, what do I want to say about this? The red, the deep red with the black dots on it are places where we're pretty confident are going to get less rainfall. Okay? This number probably doesn't mean anything to anybody, and I don't need to tell it what it means. So the places you see are Central America, Southern Europe, Northern Africa, Southern Africa, and that's about it. And the other places we see increases in rain are the dark blue places with the spots, which are kind of coastal Alaska, maybe Scandinavia up there, in places where nobody lives. Okay? Okay. All right. So now, other projected changes, just really quickly. Heat waves and droughts will become more severe in both their length and amplitude. By 2100, the global average sea level will rise by about 20 inches. right? And that's mostly because if you heat water, it expands. And if you expand water in the ocean, it's got to go somewhere and it goes up, right? But there's also melting glaciers, and there's also the net loss of mass on Greenland and Antarctica. So by 2100, the surface ocean will be about 3 times more acidic than the pre-industrial ocean. These are all things that are really well understood and kind of unavoidable. After we stop emitting, the climate will continue to warm for many centuries. It's something you can talk about over coffee afterwards. Okay? And therefore, sea level will continue to rise for many centuries. It'll take many thousands of years for nature to kind of restore this back to pre-industrial levels. Okay, let's talk about, before I run out of time, impacts on food production. Okay? Precipitation. Like I said, there's not much we can say. We know there's a place in the world where it will be reduced. Here's Scandinavia. Here's kind of the Arabian Peninsula, the Horn of Africa, India. And what this shows here is how the wintertime and the summertime rainfall will change at the end of this century compared to the end of last century. These darkest black here are 50% reduction in rainfall. This is the wet season, by the way, in this region. And here's like 20 to 30%. In the annual mean, you're talking about a reduction in rainfall about 20 to 30%. For reference, the Dust Bowl was about 7%. Okay, so this is huge compared to any human experience. And it happens every once in a while for short periods of time, like it did at the end of last century. There was a 3-year period where there was a 30% reduction in rainfall in the stands. Okay? Iran, Afghanistan, Pakistan, Tajikistan. Right? All this arc here, about 20 to 30% reduction. And if you look at what happens there, in Iran, 80% of the livestock was lost and 30 to 75% reduction in wheat and barley. Afghanistan, again, you're talking about like 50% of livestock lost. This is a part of the world where agriculture doesn't go out, bale a block of hay, put it in the barn, right, and feed the cow, right? This is a place where they're just grazing, and if you have less rainfall, you have less healthy grazing areas, and so livestock die. And livestock are really important both for income, food, and wealth, actually, in this area. Okay, so by the end of the century, the similar water stress on agriculture will be the norm throughout the tropics and subtropics due to climate changes associated with increasing CO2. Temperature. So there's not a lot of places we know about precipitation change we're confident in. And the first time I went to a meeting with the seed breeders and the people that were working on new varieties that we might need like in the future due to climate change, I came with a few slides I could talk about precipitation because that's what I knew about. I grew up on a dairy farm in upstate New York, and what we cared about was rain. Did we get too much, too little? Did it come at the right times of year? We didn't actually really care about temperature. You'll see why in a second. The first day of this meeting, everybody, the plant breeders and the seed guys, were all talking about temperature, and I thought, this is really strange. Why do they care about temperature? It's all about precipitation. Well, it turns out it's not. It turns out it's mostly about temperature. And I didn't appreciate this growing up in upstate New York. Okay, so here's again a picture, the same picture, only just for summertime, northern hemisphere. I show this because the average crop grows for about 3 months. So the 3-month average temperature change increase at the end of the century under this split the difference emission scenario is about 3 to 4 degrees. Okay, so the crops will be grown on average 3 to 4 degrees higher temperature. Okay, so nature's actually done this for us. France, 2003. Anyone remember this heat wave? Okay. The average temperature over Europe for the whole summer was 3.6 degrees, which is right what we expect at the end of this century, right? If you look in France, well, it killed about 30 to 50,000 people in France and Italy. Italy, third drop, 36% drop in the maize yield. France, 30% decrease in maize yield. 25% decline in fruit harvest. 21% reduction in wheat yields, right? If this was due to precipitation, this would happen every 3 years. This was pretty much a normal precipitation year. This is all heat stress, okay? So by 2100, years of similar temperatures will be the norm. That's the most likely scenario at the end of the century. Now, this is a little bit complicated plot. It's a different plot. What's plotted here is a histogram of summertime temperatures in France, where 0 is normal. And this is just the number of summers in the last 107 years when I did this calculation. The number of summers that were normal, and the number of summers that were 17. If I take all the summers between, say, half a degree within normal, I end up with 55. I end up with more than half the summers within half a degree of normal. And a really, really cold summer was 2 degrees colder than normal, the coldest summer on record. Up until 2003, the warmest summer on record was 2 degrees above normal, and then here's 2003, right? That's why it was such a shock. It was like so out of bounds compared to anything that had been experienced. If you look, there's the punchline. So what I did is I assumed that the natural variability, the year-to-year variability, doesn't change, but you just shift the mean. And every climate model tells you the mean shifts at a different amount. And I just collected all the climate models and said, what if the variability doesn't change, but I'm just shifting where the mean is? So it's just a new mean temperature, but it's the same year-to-year variability. And I just calculate, okay, what does that distribution look like for 107 summers at the end of the century? And that's what it looks like. So we know this already. The most likely scenario is it looks like 2003. And there's like 1 chance out of 100 that it's going to look normal. And there's also 1 chance out of 100 it's going to look like 10 degrees Celsius above normal, which puts you dead center in the middle of the Sahel. I'm sorry, the Sahara. Yeah. Okay? This isn't good if you want to grow crops in France, okay? Or even live in France, actually. If you do the same thing in the deeper tropics instead of in France, well, the tropics are famous that they don't have any variability in temperature, right? So a really cold year was a half a degree colder than normal, and a really warm year was 0.75 degrees above normal. And here's what the distribution like in the future. What are the odds that the temperature at the end of the century is going to exceed the highest temperature ever recorded? 100%, right? The odds at the end of the century that even with this kind of split the difference emission scenario, even with the wimpiest climate model that gives you the smallest climate change with increasing CO2, the odds of exceeding the highest temperature ever recorded is 100%. And I can show you plots for every place in space in this, but instead I'll show you a map. The map here is just a color and just says, what are the odds that your place in space is going to exceed the highest temperature ever recorded in the summer? And if you're red, you're basically close to 100%. And you can see pretty much everywhere in the subtropics, north and south, the odds of being out of bounds, something beyond anything ever recorded, is pretty much 100%, even with a split this difference emission scenario in a wimpy climate model. Okay, what does this mean for food security? This is a plot of temperature. This is actually Yaqui Valley, Mexico, just south of here. I don't know how far. I went there once by plane, and actually a couple times. It's the home of the Green Revolution, where wheat yields went from 1 kilogram per hectare to 3 kilograms per hectare. And this is just a measure. So this is controlled environment. It's irrigated. It's got plenty of nutrients. It's got way too much pesticide, actually. And this is just a measure of what's happened there in these controlled environments where the plants have everything they need in maize. And you can see each one of these dots is a year. So basically, you just see this trend. The growing seasons that are cold have 6 tons per kilogram, and summers that are really hot have 4.5. And it's a pretty nice line, right? The effect of fit is 10%. So for every degree C you reduce yield by 10%. Now you can do the same thing in the Philippines, and they have done it with rice under controlled conditions where nothing is lacking for these plants, and the temperature is just going up and down naturally. And it turns out you get 17% loss per degree C increase. You can do the same thing in India in wheat, and you find out it's 15% loss per degree C increase in temperature. These are controlled environments where there's nothing else limiting. If there was water limiting, it would be even worse. If there was fertilizer limiting, it'd be even worse. Right? So this is kind of like the best case scenario. All right. Here we go. So here we are. The odds of exceeding the highest temperature on record are pretty much 100%. We know these changes are under 3 to 4 degrees. Okay, so if we just look at this, then we have maybe. Oh, well, I'm going the wrong way. I was going to say that slide. Okay, yeah. So why? So this is why in upstate New York I didn't know this. If you're beyond the optimal temperature for growing a crop, then as you increase temperature, 4 different things happen. One is the plant grows faster and stops growing. All the grain fills out at the end of the growing, right? So basically, the amount of grain that actually is stored in the head is less when it's growing under hotter temperatures. It's also true that the spikelets that actually grow the grain are less fertile. It's also true that they have increased water stress, and they increase respiration faster than they increase photosynthesis. So there's lots of reasons why you expect this. Why I didn't know this in upstate New York is because we're near the optimal temperature. And if I wobble around from the optimal temperature, I don't wobble far. Right? So I don't actually see the effects of temperature. But if you live in the tropics and subtropics, you're well beyond the optimal temperature, so as you increase, yields just go down. Right? Especially important for all crops, but especially for wheat, rice, and maize. Okay. Here we go. So impacts of temperature. 3 to 4 degrees C increase, minimum reduction of 10% per degree C. End of this century, how much reduction we have? 3 to 4 degrees, 10% per degree, 30 to 40%, right? Under optimal conditions, no water limitations, no nutrients. Okay, so reduce yields of wheat, rice, and soybeans in the tropics, should be maize there too. Approximately 10% per degree C, and that gives you a 30 to 40% decrease in 2100 in India, Southern Africa, Middle East, anywhere in the subtropics between 35 degrees north and south latitude. Increased volatility in crop yield. So this is where, actually still I think most people think that the US is kind of immune to this for a really long time because we are close to that optimal temperature, right? Whereas in the tropics, you're already well past it, right? But it turns out that that's not the key. All right, so this is a typical thing you see for any species, even me, right? Where you can say, well, this could be like fitness of me, like how good I do in life. And I have some optimal temperature. For me, it's probably more like 15 degrees Celsius. It's not, I wouldn't do too well in Tucson. Okay? Maybe I'd adapt to it. I mean, that'd be, yeah, okay. But for most plants, it's about 26 or 27 degrees Celsius is the optimal temperature. And if you get colder than that, it's not so good. And if you get warmer than that, it's not so good. And pretty much all things have this asymmetric curve where once you start getting warmer, it drops off really, really fast. And there's good reasons for this that have to do with basic physics and biophysics, I should say. Okay, so now I put myself in upstate New York growing up, and there's my average temperature, and there's the natural variability. I'm wobbling around, and you can see, even under a cold year, I get 90% of my perfect yield. And even under a hot year, I get 90%. So I actually don't see a big change in yield. Okay? Small. And you don't worry about it. Great. Okay, but now if I just warm up a little bit and I'm living in the mid-latitudes, I shift myself out to here on average. And I still have the same natural variability, but now I get, if it's a cold year, I get perfect yield. But if it's a warm year, I get 0 yield. See the problem? So the volatility, not just because the mean is shifted, is because the mean is shifted and you still have the same natural variability in climate, means that yield volatility is going to go through the roof. Okay, so this is a really serious problem for all of the breadbasket countries in the world, the US, China, Ukraine, Europe, okay? That produce most of the grains in the world. Okay, here's an example. Here's Iowa today, okay? If they plant May 1st, you put in corn, and here's the average yield today, and this is like one of those histograms again. The most likely scenario is that you're going to get your average yield, right? Uh-oh. And there's only a really small chance that you'll get low yields. And there's a little chance here that you'll get high yields. And in fact, Iowa, like upstate New York, is actually on the cold side, right, of the optimal. So as you warm a little bit, you actually do better for a little while, okay? If instead of planting the 120-day variety, which I want to plant because that gives me the most yield, I say I need an insurance policy just in case it's a really hot summer, I can plant a 90-day variety, and yeah, you reduce the volatility a little bit. The reason why you wouldn't want to do this is because even under the best yield you can do with a 90-day variety, you don't get as much yield as the 120-day variety. So in fact, that's what we did growing up. We planted like 80% of our crop is 120-day and 20% 90-day. So yields are near the optimal, there's little variation. Now we're just going to add a 2-degree average warming to this and same natural variability and look at what happens to maize yields. So here's, first row will be 2 degrees warming, and you see, boom, Now, you still, most likely scenarios, you'll be near normal. In fact, a little bit better normal, because a little bit of warming puts you on the optimal. Okay? But the volatility starts getting really big. Right? And if I say plot the 90-day variety, I don't improve things that much. The odds of getting like a 40% reduction here are kind of going away, right? But I still have increased volatility compared to today. And if I go to 4 degrees warming, it's a crapshoot, right? I can get 0 yield, I can get a normal yield, I can get a little higher yield. But the odds of getting a normal yield are really low, right? There's more of an odds that you're going to get a much lower yield, right? All those blue bars down below at the bottom end add up to a lot of times, right? Okay, so let's summarize this. Today, if I look at the average yield, and I say, what's the average loss of the average yield? Well, it's 0, right? The average yield is the average yield. And I say, what's the odds of, say, experience a 10% loss due to the natural variability in temperature? And the answer is, well, I expect to see it every 9 years or so on average. The odds of seeing a 20% loss are every 25 years. The odds of seeing a 30% loss are every 50 years. It's every 2 human generations. So you don't worry about temperature today, right? The volatility due to precipitation is much bigger than temperature. But now, let's go out here and we say, as you go out and you say, well, at 1.5 degrees on average above normal, the average yield is only 5% lower. That's not bad. And this is why, until really recently, we thought this was not a problem in the mid-latitudes. Even when you go out to 2 degrees warming, you're still only losing 10% on average. But let's look at the return time, how often you lose these things. So if you look here, it's say 1.5 degrees, which is what we expect in 2035. That's 20 years from now. You expect to lose 10% every 3 years and 20% every 14 years. If you go out to 2050, right, you expect to lose 20% every 2 years and 30% loss in your crop every 5 years. And then this is on top, this adds to the precipitation variability, right? This is in addition to what we already have in terms of, so you cannot do agriculture in the United States the way we do it today. No farmer could withstand this amount of volatility in year-to-year production and stay in business. Okay? In the United States. Okay. So one other temperature effect here is what it does to pest populations. And I'm just going to show you this slide really quickly. There's every year, you lose a certain amount of your potential yield due to bugs, eating your crop. In the United States, typically that's about 8% or so of your crop in maize, say. And that's a typical number for a developed country in the mid-latitudes, France, Ukraine. I think China's a little bit higher loss. If you just increase temperature by 3 or 4 degrees over the land, by 3 degrees global average, and you say, well, how much increase in loss will I have due to pests at the end of the century? And that's what's colored here. And red is a 40% increase. So I expect in mid-latitude regions, United States, Europe, China, basically, losses of wheat, maize, and rice yield to increase by 30 to 40% because of increasing pest pressures. Bugs do better under high temperatures in mid-latitudes. The other important point here, let me just work you through one plot here. This is the amount of yield we get per hectare, per acre, how much crop you get, how much grain you get. And this one is, help me out here, I can't see this close to the stage, maize, okay? So, for example, in the United States, we average 7 tons per hectare of maize you take off. And the other thing to point out here is that the size of this bullet is telling you about the total production in the country. So the bigger the bullet, the more of the world's grain they produce in that grain. So the United States produces the most corn in the world. China is second. What's plotted here on this axis is the increase in the loss of crop due to increased pest pressure. So the point here is that the countries that produce really high amounts per hectare and the most grain in the world suffer the biggest losses in pests. That's true here for maize, it's true for rice, and it's true for wheat. And these are for really basic metabolic reasons in ectotherms, cold-blooded animals, okay, which are pests, right? Okay. So the percentage increase in yield loss is greatest where the yield is already the highest, and most grain is produced in the world. Okay. So let's, I'm going to summarize those points and put a few more things on the boards we're pretty sure of, but are harder to quantify. We know kind of a minimum estimate under optimal conditions of a loss is going to be on the order of 10% or more per degree C increase. We know that pest estimate, right? It's not 5%, it's not 500%, it's on the ballpark of, 20, 30, 40%. Okay. So these are the impacts on agriculture due to, seemed like there was something else I was going to say there. Let me think what it was. Well, okay. So many crops in the tropics and subtropics are already well beyond the optimal growing temperatures. So increasing temperature, we expect yields of wheat, rice, soybeans, maize should be on there as well, reduced by 10% per degree C of warming. Yield reductions of around 30 to 40% in 2100. That translates to that in India, Southern Africa, Middle East, pretty much anywhere between 35 north and south where you're going to grow these crops. By 2050, you'll have increased volatility of crops in mid-latitude breadbasket countries, the countries that produce most of the grain in the world. US, Europe, Ukraine, China. Loss of arable land due to salinization of groundwater. So as you increase sea level, if you're in a coastal area, you put more pressure on the water that pushes inland, and that's saltier water, so that the groundwater is more salty, and that's not good for a plant. So you'll lose some land due to that sea level rise. Water stored in snowpack will go down. And this is even if precipitation doesn't change. If the snow line, where it changes from snow to rain, increases, the area that you can actually capture snow in a mountain goes down. So this is particularly important in a place like the Sierra, the Cascades, where irrigation using the snowpack, the snow that falls, is really important for crops. Increased crop loss due to increasing pest pressure. We just talked about that one. Decreased nutritional content of grains. When you grow grains under higher temperature, the protein content of the grain goes down. I'm not going to try to explain that. Next week, Russ Munson is going to do a phenomenal job on this, and I'm going to leave it to Russ to explain that. But it's also true that when the protein content of the grain goes down, right, then the grain is more susceptible to disease. Now, increased disease transmission rates. Bacteria, viruses do well under high temperatures, right? So the transmission rate of diseases that affect these plants will increase. Okay, impacts of changing precipitation. By 2050, many in the subtropics will feel impacts of changing precipitation. We talked about rainfall in Africa, the Caribbean, Central America, the Middle East will be reduced by 10 to 20%. The frequency and duration and intensity of drought will increase. Flooding will increase in both the mid-latitudes and the tropics. Okay, so those are just the climate impacts we're pretty confident in. The impacts on crops are crop yields will be reduced, and in some places staple crops will have to be abandoned. I really want to talk about this, but I'm running out of time. Shorter, more intense monsoons. It's kind of interesting. This is not something that I think we understand well, but every climate model tells you the monsoons will be more intense. We understand that. There's just more water vapor in the atmosphere in a hotter climate. But what we don't fully understand is that everywhere we've looked, monsoons are shorter. In a place like Indonesia, the monsoon today is just long enough that you can plant two crops of rice. If you make the monsoon shorter, you can't. And that's what happens in an El Nino year. Like this year is going to be a really bad rice production year. In Indonesia, anyone got any money in this? Actually, not much rice is traded in the open market. But what happens then is you can't grow that second crop, and so you basically, food supply for the country goes down. Indonesia is the fourth most populated country in the world. Rice is a staple crop, and it's a poor place, relatively, right? So this is a big problem for Indonesia in 2050, not the end of the century, but really soon. More nutrients will be leached from the soil. If you have really intense rainfall on drier soils, it tends to leach nutrients out more, and that's not good for plants, losing your food. Climate change will decrease soil organic content, which is also the food, right, for food for plants, and impact the soil biogeochemistry. And the last one here, which it turns out, for agriculture anyway, increasing carbon dioxide, people often talk about, well, carbon dioxide is a food for plants. Plants should be happy. Well, it turns out that, yeah, plants are happy, like weeds, right? So they compete for food with corn. And the other thing is you have the temperature effects associated with increasing temperature, and those are all on the downside. And very quickly you find out that increasing carbon dioxide does not give you this food for plants, right? It's a net loss very quickly everywhere on the planet. And there's many, many more impacts on managed ecosystems and wild ecosystems that Russ is going to talk about next week, so I won't go there. And besides, it's not my expertise. Okay. Let's go back and think about what this means for the food insecure, right? Go back to this picture. These are the places where you have the billion people on the planet that are malnourished today. These are the places where people really depend on agriculture for income, to buy the food, and to eat and growing the food. It's the places where countries have the greatest growth rates. Almost all of that extra 2.5 billion people that we're going to add to the planet are going to be added to those countries. They're poor, they depend on agriculture, and they're the regions that are most stressed by global warming, right? Just look at, right? So the estimates are hard to come by, but you end up with, sort of like another 200 to 400 million people that are malnourished, right? So this is not a problem that's kind of out at the end of the century. It's a problem that's like, 2050. It's a problem that, will I live to see it? Maybe. Certainly my kids will, right? It's only 35 years away, right? So let me just end on one optimistic note. I've given this talk a few times, and everyone says, well, it's like, doesn't it, you're going to commit suicide now? It's like, no. Despite what I said about utopia, I went to the Paris meetings this year. What is remarkable is the whole tone of the discussion has changed. Not in the United States, Washington, D.C., but actually even in the United States, Washington State or Iowa, and certainly in other places of the world. And the most important thing is you go to this meeting and it's about climate change, what do we do? And everyone put on the table voluntarily emissions. So there's actually no really things you have to do. But I was struck because I expected nothing out of this meeting, really nothing to come away excited about except eating for a nice week in France, right? In Paris. But in fact, really important mainstream economists were up there and saying, here's an opportunity. We got to jump on this. It's an economic opportunity. And everyone put their kind of proposals for what they plan to do country by country in terms of reducing emissions. And everybody, I think, left that meeting thinking that we're going to come back in 5 years. That's an important part of the protocol, or the agreement, that every 5 years you come back and say how well you did and what you're going to do next. I think everyone left that meeting thinking like, we are going to turn this thing around really fast because there's just huge economic opportunities to be had here. And technologies are moving ahead really fast in alternative energies that it's not inconceivable that we might not double CO2. I mean, I guess if I was a betting person, I would still bet on it. But I had to almost think like, well, is it really utopia anymore? It actually is not out of the question. It's hard, right? Re-plumbing the whole world economy on alternative energies. Or if you burn fossil fuel, that you're not going to let it go in the atmosphere. So you capture it before it goes in the atmosphere. Those are all technologies that are still pretty young to do that kind of stuff, and they're pretty expensive. But there was, I think, an optimism there that really struck me as being something I've never seen since the 1970s, actually, in this country. When I was in college and we had Earth Day, it was very weird. There were people on the streets, young kids on the streets, that were there, and there was like signs on the Eiffel Tower. And I was so struck by this, I stopped going to the meeting and started going around interviewing the people in the streets and saying, why are you here? Why are you, so happy about this with, alternative renewables and stuff? And it's a different energy. And we might not see it quite yet in the United States, but things are turning around quite fast. I know what the last point was. I'm sorry, I'm running out of time. But one more question. The only option for avoiding this increased volatility or the decrease in yield is to create varieties that are where you're moving the optimal temperature as the mean temperature changes. That's something that actually, it turns out, the wheat breeders of the world and the maize breeders of the world have been working on for 30 years with no progress. They've known about this problem, and in terms of heat is a very, very, very difficult thing to breed for, and it's not as easy as the Green Revolution. It's not going to be there's new varieties, most likely. If you bet on that, that's probably a wrong bet. Thank you so much for coming. And right, one more thing. And really, I want to thank the dean. I want to thank all you guys for being. I've never experienced thousands of people listening to a science lecture. It's awesome.